All right, let's begin. As you can see, the normal projector is back in action, so that's nice. We'll be able to use the document camera when needed to go over solution illustrations and things. So we're not going to meet as a class on Thursday, and that'll complicate things a little bit for the homework assignment that you need to submit. Homework 9 is due by noon on Thursday, and so what you're going to do is you're going to put it in this folder, which will be in the box that's hanging on the wall right beside my office door. And then the grader is going to pick those up right at 12. We're going to go over an illustration today on how to use that zipped shape file that I emailed you yesterday, just in case you're having any trouble with that. But that's a part of the assignment, and so submit it by 12 o'clock, and the grader will collect it and begin scoring that assignment. So I originally had thought that we would have an online lecture for Thursday, but I was able to consolidate the topics for today and Thursday's lecture into just this class meeting. And so not only will we not meet on Thursday, but there won't be a recorded lecture either. Instead, I'd like you to get started on the project area selection handout that I've just given you. You can write next to where it says project area selection, you can write homework 10. At least I think that's right, yeah? What you're turning in on Thursday is homework 9, yeah. So this is going to count as homework 10. Basically, I want you to have a chance to apply the principles of hydrology we've learned this semester in a watershed that you're interested in. And I use the word interested loosely. Maybe you're not interested at all in any watershed anywhere, but I know some of you have family property that maybe you'd want to find out what are the flow rates going through a certain creek, things like that. And so what this handout is a chance for you to start gathering data for the watershed that you're going to use. I won't say interested anymore. The watershed that you're going to use as the subject of this assignment. And so steps 1 through 5 is just a way of you estimating the area of the watershed, gathering some land use information and soil type information. And it just relies on using Google Earth, which you can install for free, and I think is already installed on these lab computers out here. Using aerial photos to look at what's there and estimate what's the land cover. You know, is your watershed 100% asphalt area, or is your watershed scrub oak, and so on. And then also collecting some of the soil type data for that area in the same way that you will for this week's assignment. So as it says here on the handout slide, I'd like you to bring this to class on Tuesday, November 4th, but you don't actually have to submit it to me until November 6th. But on November 4th, I would like to see where you're at. So we'll have some somewhat informal time on Tuesday when I plan to go around and see how much of the data you've gathered already. And then I'll collect it to score on Thursday the 6th. All right. So we're entering a phase of the course that's a little bit more flexible than it has been to now. Remember, at the beginning of the semester I told you that we had to learn a lot of foundational information before you'd really start to do practical calculations, and we're finally at that stage where you can actually start doing hydrology with what you've learned. And so some of our class meetings will be less lecture and will be more working through demos and learning how to use software. And so this Thursday, obviously we don't have class, but then in a couple of weeks we'll also have some somewhat flexible class meetings where it's not just all lecture oriented. So just to summarize, your assignment due on Thursday, put it in this envelope. Any questions about that? All right, let's take a look at the web soil survey, and then also I wanted to show you very briefly how to measure an area with Google Earth Pro. Because on the handout I've just given you for the project area selection, I ask you to estimate what's the watershed's area. So if you haven't already done the web soil survey, one of the things it wants you to do is to define an area of interest. Okay, so I'm copying this link and I'm going to paste it into the browser here. And it takes you to a graphical interface that's basically just a map view of the United States. And you can define your own area of interest, and that's what you'll have to do when you're working on the project area part. But importing an area of interest is very simple. You just go here to import AOI, and then you're going to create it from the zipped shapefile. That's what I emailed to you. So you click on that, and you browse to the location of the area of interest. In my case, I saved it onto the V drive, and it's area of interest shapefile. It takes just a moment for it to load, and then it will automatically zoom in on the project area. So you can see this is here in Cabell County. It's a certain watershed where I want to gather the soil data. And the rest of the instructions tell you where you can identify the hydrologic soil group is what we're most interested in. And these tabs across the top allow you to get to the data that you'd need to identify the hydrologic soil group and actually what the name of the soil is, because the soils are named something more descriptive than just A, B, C, D. They have names based on the age of the soil and where it comes from and so on. So I just wanted to show you how to create an area of interest. Now I'm going to clear this area of interest, and if you need to define your own, like if you don't have a shapefile already, let me just zoom out a little bit so we're in a different zone. Then you can define an area of interest. Let's see, where was I doing that? Area of interest, interactive map, just yesterday. Okay, here it is. All right, so you can either make a rectangle or you can trace your own polygon. So if I went into Google Earth and I found out that my watershed that I'm interested in is over here, then I can use this polygon tool and click around the boundaries of my area of interest, double click at the end, and then it sort of delineates that zone in the same way that it did when I had imported the zip file. So now I can go across these tabs and gather the data that's just going to be within the cross-hatched area that I've defined through interactive clicking. Any questions about web soil survey? I don't want to go through the whole process of showing you where to get the names and the reports, because all that information is given in the homework handout, and I want you to get the experience of going through that. Well, let's take a look now at the Google Earth Pro demo, how to measure an area. I don't have Google Earth Pro on this computer here, but I do have it in my office computer. And so if we zoom in on Cabell County, how am I going to measure the area of a watershed? Let's say that I'm interested in, I'm going to tip it by holding down the center button. And if you hold down the center scroll button, it allows you to sort of see the texture of the land a little bit more. And as I rotate, you can see that here's a ridge line. And that ridge line defines the boundary. And there's a stream here, because that's the low point in the ground. And raindrops that fall on this side of the ridge line will go to that stream, and raindrops that fall on this area are not going to flow into that stream. So if I wanted to estimate the area of this watershed using Google Earth Pro, it's going to be an approximate thing. Let's say that I'm thinking about putting in a culvert right here at this junction. So I want to know what's the area that feeds into that zone. So I go up here to the tool that says Add Polygon, and then I'm just going to start tracing the boundaries of the polygon. So I think that if a raindrop falls here, maybe it's going to flow down here, so it wouldn't be to my junction. I'm going to start here and go straight up the hill along the ridge line. And this will give me a rough estimate. Here under measurements, it tells me that the area is 0.1 square miles. That's, maybe I want to know acres. So 38.6 acres would be my estimated watershed area. That's just maybe better than an order of magnitude, but we could call it like a back-of-the-envelope type of a calculation. It's something you can do so quickly you don't need a lot of resources and don't need a lot of time. When we start learning WMS, we're going to have a much more sophisticated and accurate way of measuring the watershed area. And I'll introduce WMS to you next week when we get together on Tuesday. But this is maybe a way to get a feel for the watershed by having to spin around and see it from different angles. There's actually, oh, how do I clear that? There's actually a way of, it'll eventually land you on the hill and it'll start to give you the ground view, which I think is pretty interesting if you double click on it. So now that's the view that you'd have if you were standing on the hill. That's, I think, pretty amazing. Maybe it works best when you've got a tall mountain that you're on, but. All right. So does everybody feel comfortable with how to import the zipped shape file and also how to measure the area using Google Earth Pro? All right. I emailed you the info you need for Google Earth Pro, like the license key and serial number. So you can install that on your own PC if you'd like to have it. If not, you can just use the lab computers. All right, so where we left off was talking about curve numbers. Does anybody remember what curve numbers try to define? What's the point of curve numbers? All right. A high curve number goes along with what? And a low curve number. If you have a high curve number, what would you expect? What kind of environment would be associated with a high curve number? What's that? Okay, poor soil. And there's some, it could be a really good soil and what? All right, poor soil, urban conditions. Right. And what you'll recall is that there was a table of curve numbers we looked at that had different land uses and soil types. And that is what defined our curve numbers. Where was that? Here we are. All right, so the columns A, B, C, D, those refer to soil types. And soil type A is a good soil that's well drained. Maybe sandy soils have high conductivity and would be classified as an A soil. C and D soils have lots of clay and are poorly drained. And so you'll notice that you'll have higher curve numbers for the poor soils, class C and D, compared to the good soils, A and B. And it's strange for us as engineers to be applying value judgments to these soils, where we're calling C and D bad soils and A and B good soils. Why are we applying that value judgment? Aren't we supposed to be impartial? Like, why is it that we think A and B is good? What's the perspective that makes us apply that judgment of good versus bad? What do we want? Okay, we don't want a lot of what? Okay, we don't want a lot of water held up. Why? Why don't we want the soils to delay the flow of water into the soil? We want to find the runoff. That's true. Really, runoff for us is a problem. All we see when we see runoff is damage to structures, expensive big pipes that have to be put in. So really, the engineering perspective is that this runoff, the storm water, is kind of like waste. And we would prefer that there's as little of that storm water that has to be accommodated as possible. And so that's why we call C and D. We think of those as like kind of bad, unfortunate soil types. Oh, I've got bad news. You've got class D soil on your property, is what a hydrologist might say to a landowner. And the landowner would say, I guess that means I have to put in a big culvert. Because if that landowner had had good quality soil, an A or B soil, then there'd be more infiltration, and so the structures required to accommodate the stormwater runoff would be less substantial. So just a side tangent about what is our perspective when we are doing most of these evaluations. Our perspective is that the runoff water is unwanted, it's a waste, it's just going to cause problems. Now, of course, on the other hand, we know that, well, Runoff is important for watering plants, it's important for drinking water, but in a big storm where there's a big flash flood, that peak of flash flood water, the high point of the hydrograph, this part you're not using for irrigation and water consumption. It's the steady base flows that are always there that's the useful part of the water. So anyways, all right, so back to curve numbers. A high curve number means you either have urban conditions or poor soils. And so look at streets and roads. If it is street and road, meaning asphalt or concrete, it doesn't matter what your soil is. You're going to have a high curve number. But if you have a nice forested cover or lawns, look at how low the curve numbers are for parks, golf courses, cemeteries. Very, very low curve numbers. And so curve numbers are similar to the runoff C value in the rational method, but we were looking at how to calculate storage from curve number in the examples last time. All right, so we're talking about curve numbers, and oftentimes the watershed will have more than one curve number in it. And so we have to calculate sort of an aerial average curve number. So there were several people that weren't here last time. This will be a good first exposure to how to use curve numbers, and for the rest of you it'll be a good reminder, I think. I'd like you to calculate how much rainfall excess will there be in a storm that has precipitation of 6 inches. This is our watershed. Our watershed is 40% having soil group C, which for this type of land cover that we have yields a curve number of 83. We got 25% of the watershed is curve number 80, 20% curve number 94, 15% curve number 93. All you need to do to calculate the average curve number for this watershed is multiply the fractional land use quantity by the curve number. And so it's just a weighted average. Calculate the weighted average curve number, then you can find the storage. And once you have the storage, you can put it into this formula using the precipitation P is going to be 6 inches, and what we want to know is the rainfall excess, or P sub E, is essentially how much runoff there will be as a result of this storm. Okay, so go ahead and calculate that, and then I'll put the solution on the board. Yeah.
In the homework, you want to know what the runoff volume per unit area is.
Mm-hmm.
Is it the same?
Well, this is the runoff depth per unit area. And so if I wanted to know the runoff volume per unit area, I'd say, you know, this depth times an acre would give me, you could calculate, an acre is 43,560 feet, and this convert it from inches to feet. And so I could find a volume, meaning cubic feet per acre. So this isn't yet a volume, this is a runoff depth. Does that make sense? Okay. Uh-huh. No, not always. But it sort of raises eyebrows when you express it to like as a decimal, because even though it's more objective than C values, it's still seen as sort of a little bit subjective. And so, like if I said, in this case, what's the decimal version of it when you calculate the average? 80? Yeah, if I say 85.95, a hydrologist would say, oh wow, you really think you know a lot about that watershed, because, you know, who's to say that exactly 40% of it is the curve number 83, and you know, if the concrete has cracks in it, maybe it'll absorb water versus if it doesn't. And so, you know, to write out that level of precision would maybe imply that you've got more information than you do. But when we are doing WMS, that will usually express the curve numbers to a single tenth place for decimals. So it would say like 86.0, since it would round off the 0.95 up. Yeah. So this is pretty straightforward, and what you have to do manually here will be done automatically when we start performing watershed modeling using WMS. So rainfall excess is just that fraction of the precipitation that doesn't infiltrate and isn't abstracted. So where's the rest of the water? We had 6 inches of rainfall, so precip was 6 inches. What we find at the end is that 4.41 of those 6 inches is going to run over the surface, and the remaining 1.59 inches of rainfall is either surface wetting, infiltration, interception, or other abstractions. So all of the water has to be accounted for. Here's an illustration that shows sometimes it's complicated what a watershed looks like. And in this watershed, what we have is pervious area upstream and impervious area downstream. So it's sort of like we've got a grassy area that's adjacent to a parking lot. Here, impervious would mean, like pavement, for example, with a curve number of 98. And how the pavement is connected to it, the adjacency of pervious and impervious pavement kind of changes how we can calculate the composite curve number. It's not just a simple average, and I think you'll see why in just a minute. We've got this figure here that helps us to calculate what the composite curve number will be. In some cases, the figure is just a graphical way of doing that simpler average, but in others, it's not. So we're going to have this first example. We're going to call it connected impervious area, because the impervious area is directly connected to the outlet. In the next example, we're going to flip these two. We're going to make it so that the impervious is upstream from the pervious. But in this first one, it is directly connected impervious area. Directly connected, and by that I mean to the outlet. Okay, so the connected impervious area is 3 acres, and the total area is 3 plus 7, 10 acres. And so the percent connected impervious is 30%. 30% of the entire watershed is directly connected to the watershed outlet, and that's the impervious area. The pervious curve number is 60. Okay, so we go along this chart and we find on the x-axis where it says 30%, because our connected impervious area here is 30% of the watershed. And if you follow that up to the pervious curve number, we've got a grass of 60. So we want to find the intercept between the 30 and the 60. So what I mean is follow this 30 upwards to intercept the curve number of the pervious area. And here it says that grass, the rest of the watershed is grass at 60%. So go up, intersect with the 60, and then go to the left, and that says the composite curve number is 72. So from the graph, where the x value is 30, intercept the 60 curve and follow to the y-axis. And the value at the y-axis is 72. Well, that's exactly what you'd get if you did the process that we just followed of finding the average curve number. You know, we've got 3 acres at a curve number of 98 plus 7 acres at a curve number of 60, and that's a total of 10 acres, and the average is 71.4. So essentially equivalent to what we guessed at with the figure. We couldn't get a decimal point. It looked like about 72. So it's a simple situation if the impervious area is directly connected. But what's more complicated is what happens if the impervious area is upstream. So what do you think the complication might be for this? Why isn't this as simple as when the impervious area is already connected to the outlet? What can happen to the runoff from the pervious area? No, let's see. It's still just the 3 acres. So 3 acres is impervious, 7 acres is pervious. All we did was we changed the location. We moved it from being directly connected to the outlet, and now it's upstream of this grassy area. So the runoff from the parking lot has to flow over the grass before it gets to the outlet. Okay, yeah, that's exactly right. Here, there was no opportunity for infiltration. All of the runoff goes to the outlet. But when the impervious area is upstream of someplace where there can be infiltrated, then a fraction of the runoff from here is going to go down into the soil at the grassy area. So there is an opportunity for infiltration. So you can see that there's a different figure now. It looks a little bit more complicated. We'll go through the process of using that figure. Oops. All right, so this is unconnected impervious area. Meaning the impervious area is not directly connected to the outlet. The water that flows from the impervious area has to flow over the surface of the grassy, pervious land before it gets to the outlet. Okay, so first of all, we need to find the ratio of unconnected impervious to total impervious. Unconnected impervious to total impervious. And what that's asking is how much of this impervious area isn't touching the outlet. And in our case, all of it isn't touching the outlet. And so the ratio is 1.0 because none of that impervious area is directly connected to the outlet. The total impervious area is 30%, same as before, 3 acres out of a total of 10. And so we're going to go on the figure, and we want to intersect the 30% impervious area with a 1.0 curve. So starting off with this, see where it says 1.0 here, using the ratio of unconnected impervious to total impervious. So this curve is the one that governs our example, and we need to find here the intersect of total impervious area. Ours, it's 30% impervious, and so this is our intersection point, and we're going to follow it over to the pervious curve number. Now this pervious area here, the grass, has a curve number of 60. So we're going to follow horizontally this point over until we intercept the 60 curve, and then we go down. And so we are right in the middle where it says composite is 65. So composite CN is equal to 65. So if you're following along what the logic is, the first thing is to find this ratio. Okay, so this is our curve, And where along this curve is determined by the x-axis, the total impervious area. In our case, it was 30% impervious. So this is the point, and we start following it sideways until we intersect the pervious curve number that we have for our pervious area, 60, and then we go down, and then you can see it's right in the middle between 60 and 70. So our overall composite curve number for the watershed is 65. Any questions about that? There's one more case we'll consider that's even more complicated. And that is, what if some of the impervious area is connected to the outlet and some of it isn't? Okay. So remember that when we were just looking at the previous example just a moment ago, the benefit of this is that some of that extra runoff from the impervious area is going to have a chance to go down into the grass. But here, the part that's in area 3, this impervious part here, all of the runoff from here is going to go straight into the outlet. It's not going to have that same infiltration opportunity that the A1 area will. So we have some of the impervious area is directly connected, some of it is unconnected. So that's the scenario. So how would this example be different from what we just looked at? Well, first of all, our ratio will be different. The ratio of unconnected impervious to total impervious. So the unconnected impervious is that 1.5 at the top. That's not connected to the outlet. And the total pervious area is 3.0. The total impervious area is the one on the top and the one on the bottom together. So our ratio is 0.5. The total impervious area is still just 30%. Total impervious area is still 3 out of the 10, so 30%. And if we start with this curve now, where it says 0.5, this is the curve that we have to follow. And so 30% impervious area at the 0.5 intercept, we're going to go over, and we're going to stop when we get to the pervious curve number of 60. Now here we are at the pervious curve number of 60, and we go down. And so now that curve number is closer to 70. I read that as 68. Composite CN is 68. Yeah. Then you can't use this figure. Yeah, I'm not sure why it stops there. I guess probably because there's a limit to how much infiltration can occur in the pervious zone. It's maybe above 30%. There's a nonlinear response between how much of the water can actually get down into the soil. You're like overwhelming the soil, in other words. But under 30% of it being impervious, then that grassy section can sort of help take some of the extra water. Okay, so this one was 68. What was the curve number on this example? 65. So why, if it's the same area, like it's still just 3 acres of impervious here and here, why is the curve number higher in this situation? That would be a good quiz question, like a conceptual question. Explain why the curve number is higher in this watershed compared to this watershed. There's not as much infiltration on which one? On this one. Why not? Yeah. Right. All of the runoff from area 3 goes into the outlet. None of it's going to flow over the surface and maybe get down into the grassy soil like it did in this illustration. All right, so like what are the implications of this? Sometimes here in West Virginia you'll see that they put, they'll develop on the top of a ridge line. Like Amazon, most of you have seen the call center at Amazon. And so all of that runoff, if they didn't put in storm drains, and they have, but if it was just all of that runoff was going over the surface, that would be probably going to generate less runoff in the stream than if that call center was at the bottom right next to the stream, because that's impervious area with runoff going over the surface. But you know, as it ends up, it's so steep near that it wouldn't do a lot of infiltration just because of how steep it is. But the principle is that you can have enhanced infiltration by connecting impervious to a pervious grass strip. And they're starting to do this like next to roadways. They're starting to plant grass on the shoulder of the road, even when they have a concrete lined ditch that the stormwater is going to go to. Just having a grassy swale, as they call it, is a way to increase the infiltration. All right. Like I mentioned a couple of times, we're going to start using a program called WMS. Here is the license code that you need to install the software. So write that down. I didn't want to put that on the presentation slide since I publish these widely. Only you get to use this license code. It's a program that several years ago they were charging like $3,000 per person to use, but they've changed it to an annual subscription, and Marshall pays that annual subscription. It's not as much as it used to be, but luckily for the educational license they let the students install the program for free. There's no additional cost for students to use the program. This program is not installed on the lab computers here, and so you'll need to install it on a PC to have access to it. Yeah, it's on the tablets. At least it was. We'll have to double check next time we've got them out. But yeah, it's on the tablets. We'll start using this next week, so bring your computer both Tuesday and Thursday next week, because I'm going to be doing some demonstrations in WMS, and I'm going to ask you to follow along as we do like a tour of it. And that's where you can get it. All right, the second part of what we're talking about today is an SCS Unit Hydrograph method. And you'll remember from our previous lectures, a unit hydrograph is a way of knowing how much flow there's going to be out of a watershed if you have 1 inch or 1 centimeter of rainfall. And of course, it almost never is going to rain exactly 1 inch during a storm. And so the way that this unit hydrograph is useful is that you scale the runoff response based on how much rainfall excess you do have. And so here we have a shape of some watershed response. And so we have a hydrograph shape that comes to a peak relatively quickly, and then it tapers off more slowly. And you can see down here on the horizontal axis, this is not units of hours, where it's saying 1, 2, 3, 4. That's not hours, but rather what it is it's scaled to the time to peak, T sub P. So what it's saying is if it takes 2 hours to get to the time of peak, then here you are at 2 hours, and then 2 times 2 is 4, 2 times 3 is 6. So not only is the vertical unit scaled to the quantity of the unit hydrograph, but also in this SCS unit hydrograph they're scaling the x-axis as well relative to the time to peak. And so the advantage of doing this is they found that through a lot of research that many watersheds have a similar shape of a hydrograph, meaning that it comes to the peak more quickly at the beginning of the storm than that peak tapers back down to the base flow. And so that's the common thing among all watersheds, is that the peak comes more quickly than it goes. Sometimes the time to peak is just a matter of minutes. Sometimes the time of peak may be several hours. But you can scale not only the vertical axis, which is the quantity of water, but you can also scale the horizontal axis. So what you have to do to use this hydrograph is you calculate what's known as a lag time based on the area of the watershed, the curve number of the watershed, just some parameters that you can calculate based on the physical characteristics of the watershed. You calculate the lag time. And the lag time is related to the time of peak, and I'll show you the equations for that. The lag time, as it's shown here, is it's the time from the peak to the middle of the rainfall event. And so T sub r is the rainfall duration, and the lag time is how long it takes to go from the middle of the rainfall duration to the peak. Now, the lag time is calculated based on the S, which is related to curve number. Remember that we calculate S as a function of the curve number, but also the lag time takes into account how long the watershed is, the hydraulic length. And so L, you can think of that as the distance from the outlet to the furthest most point in the watershed. The hydraulic length is, the particle that is flowing from the furthest point in the watershed to the outlet. What's the distance that that particle must travel? And then Y in that formula is just the slope expressed as a percentage. Once you know the lag time, you can calculate the time of concentration. There's a rough approximation converting between the two. It's just the time of concentration is 5/3 of the lag time. Now, there's a typical peaking factor that's built into finding the amount of runoff. The typical peaking factor is 484. And you'll see the units here that I've got listed. If we want to find out the peak discharge for a unit hydrograph in terms of cubic feet per second, then this 484 is expecting the area to be in units of square miles and the runoff depth to be in terms of inches. And so that's unfamiliar for us to see Q, because usually we think of Q as a volumetric flow rate. Like that's what's in our mind from fluid mechanics and hydraulic engineering. But now what they mean by Q is they mean what is the rainfall excess. So in other words, what's the depth of rainfall excess? Maybe they should have called it P sub E, but everybody has different variable definitions from book to book, and this is defined by the Soil Conservation Service. That's what SCS stands for. So in your notes, you can say, here, this Q, what they're really referring to is P sub E, the precipitation excess. Oh, I've got that right there. You don't have to write it in your notes. I thought of it for you. Okay, but this is just a typical peaking factor. So look at the different kinds of peaking factors. In a rural area that's very flat, the conversion would be 100. If it's a steep area that is urban, like Pittsburgh, where it's a city with lots of hills and lots of rivers going through there, it may have a higher peaking factor. And so let's put that into practice with an example here. We've got a watershed area that's 3 square miles, and the curve number is 86. We want to find out what's the peak discharge according to this SCS Unit Hydrograph if we know that the watershed has a 3% slope and the hydraulic length of the watershed is 1.2 miles. All right, so the first thing that we'll do is calculate the time of concentration. All right. To calculate the time of concentration, we start with the lag time. Okay, lag time T sub L is going to be L to the 0.8 power S plus 1 to the 0.7 power and 1900 Y to the 0.5 power. We are told that the watershed has a curve number of 86, and so we need to calculate what is S for a watershed with a curve number of 86, and S is 1,000 divided by the curve number minus 10. And this is only in traditional units. You know, these curve numbers are, the tables that you can look up for curve numbers are anticipating that you'll put it into this formula, and then what you end up with is inches. So 1,000 divided by 86 minus 10, that gives us a storage of 1.63 inches. So when we calculate the lag time, we're going to have the hydraulic length of 6336 feet, which we're told 1.2 mile hydraulic length. So L, 1.2 miles times 5,280 feet per mile. That's the conversion between miles and feet. 6336 feet. Okay. So here's L to the 0.8 power. Now S plus 1, so 1.63 plus 1, and that to the 0.7 power, 1900. And now the slope in terms of percent, that'll be 3 to the 0.5 power. Okay, what do you get for the lag time if you put those values into your calculator? And that'll be in units of hours. Good. That's what I got too. Hopefully we're both right. 6, 5, 7 hours. So if we go back to the shape of the hydrograph, what that's saying is the lag time, T sub L, the time from the middle of the rainfall excess event to the peak of that runoff hydrograph is 0.657 hours. Okay? So what we want to do now is calculate the time of concentration. Okay, so T sub C, time of concentration, is 0.67 times 0.657 hours. Okay, the time of concentration is 1.093 hours. And step 2, find the time to peak. Oh, you're right. I wrote that wrong. Thank you. Yeah. 5/3. Thanks for catching that.
On the stub, when you're doing the percentage, you'll put a decimal point,
What?
the slope.
Right. It's as a percent.
Oh, it is this.
Yeah. Mm-hmm. Yep. Yeah, so 3%. You actually need to write 3 rather than 0.03. Okay. So time of concentration we got. Now we want time to peak. Time to peak. T sub P is 0.67 times the time of concentration, which we found was 1.093 hours. That is 0.729 hours. All right. So we've got all the times nailed down. Now what we want to look at is the amount. How big is the peak going to be? We know when the water gets there. How much of it will there be? In step 3, we're calculating Q sub P, and it's 484 times area Q T sub P. Okay, so 484. The area here is 3 square miles. And then the Q that we're putting in, we're assuming 1 inch of rainfall excess. Doesn't say that, does it? What if I Find the unit hydrograph. Yeah, so unit hydrograph. Q equals 1 inch of rainfall excess. Okay, so we just put 1 inch. And then divided by the time to peak, 0.729 hours. And what that tells us is that Q sub P is going to be 1992 cubic feet per second per inch of rainfall excess. Okay, so the hydrograph looks like this. The peak is going to be 1992 cubic feet per second per inch of rainfall excess. And the time to peak, which goes from the beginning of the storm to where it's the highest that we've just calculated, the time to peak is 0.729 hours. So we go back down here where this is 0, 0.729 hours. Now this last part of the example asks, what's the flow rate at a time of 87 minutes? So 87 minutes into the storm, what's the flow rate? That seems like a strange number. Why 87? Well, I asked it that way just to make it a little bit easier to calculate. This is what that curve is based on. These are the actual numerical values that that curve's based on. So if we go back to here, there's the hydrograph curve, and then the other one is just sort of like the total amount of water as a percentage of what's going to come. Okay, the mass curve. So if you look at the hydrograph curve here, that shape is based on this table. So I'm curious to know, after 87 minutes, what's the flow rate? So what that means is at t equals 87 minutes, then what's the ratio of t versus t sub p? 87 minutes is 1.45 hours. If I divide 87 by 60 to convert it into hours, so 1.48 hours divided by our time to peak of 0.729 hours, that ratio is 2.0. So look on this table. The first column is t to t sub p. So here where it says 2.0, we follow it over and it's 0.280 for the discharge ratio. So the Q versus Q sub P, that is 0.280. So what is the flow rate at that time? What we can do to calculate it is just multiply Q at 87 minutes is 0.28 times Q sub P. So that's 0.28 times 1992 CFS per inch of rainfall excess, and that's 558. 558 CFS per inch of rainfall excess. From this table.
Oh.
Yep. Here at 2 times the time to peak, you're only going to have 28% of the peak flow rate. You know, these fractions here, if you go up to 1 at at 1 times the time to peak. In other words, at the time of peak, you're going to have 100% of the discharge. But then it tapers down over time. So when WMS is generating hydrographs for you, this is the approach we're going to tell it to use. It has lots of different unit hydrograph methods. It's got a lot of different time of concentration calculators. But we're going to use the SCS time of concentration and the SCS unit hydrograph. All right, let's look at these announcements one last time before I let you go a little bit early. Remember, no class on Thursday. Put your homework in this folder, which will be right beside my office door. Get it there Thursday by noon, because that's when the grader's going to pick it up. And did everybody get a copy of the project area selection handout? I'd like you to have it as complete as you can on Tuesday, and we'll spend a little bit of time in class on Tuesday discussing project areas and what's maybe a suitable size and a suitable location. But going through this process, I think, will help you identify a spot that later on we can use in WMS for you to complete the project. So that's it for today. I'll see you a week from today, next Tuesday in class again.